Hi, this is Gershon Wolf, and welcome to Modern Music Composition. In today's lesson, we're going to continue to talk about voice leadings, and in a little bit different format as we did in the previous lesson, which was lesson 10. In lesson 10, I explained to you what a tonnets was, and where each vertex of the tonnets is a single note, and then you would create these triangular shapes, and if the triangle it pointed upwards, it was a minor triad. If the triangle was pointed downwards, it was a major triad. This is also a tonnet style representation. They call it the chicken wire representation. I call it the hexagonal representation, where instead of each vertex being a note, each vertex is actually a chord. So you have C major. I wrote in blue the C minor. It's the only one I did in blue because it was hard for me to write a lowercase c and have it still legible. So here is E minor, E major. So where now the edges are the voice leadings. Rather than the edges before, they were connecting those notes into a triad, and then your voice leadings, you were folding over given whatever operation you were going to do, whether it be a P, an R, or an L operation. Just brief history on this. This is actually pretty recent. This comes about in the late 90s by a fellow named, I think, Dothet and Steinbach came up with this representation. And so it's kind of interesting because just once again, a brief history, it was Euler that came up with the first tonnets diagram to explain how harmony progresses through a melody. That was about 1740, and then it was Hugo Riemann who in, I think, about 1860 described it in the manner that I did in the previous lesson, in terms of how harmonies move along in smooth progressions. And now, 140 years later, these two fellows, Dothet and Steinbach, come along with this representation. So these things take time. Also, another thing to note is that, well, not only this representation, but also the tonnets representation of Riemann. When I only have a subset written here, when you actually write a much larger set, you can actually fold it onto itself and create what's called a torus. A torus is a three-dimensional structure. It looks just like a glazed donut. So next time you take a glazed donut and you take a bite out of it, you're taking a bite out of your voice leading. All right. Okay, so what are we going to do today? Well, I thought, well, since I've been talking about so many abstract things, you know, set theory, you've learned a couple chords, and I thought it was time to maybe use some of these symmetry arguments that I've been talking about, and in terms of how do you use symmetry, how do you use set theory, how do you use these chicken wire representations to create a piece of music. Isn't that what we're supposed to be doing? So I'm going to introduce another triad, and this one is called the augmented triad. And I'm just going to give its representation in terms of C major. So here's our first part of a major chord is, you know, it's going to be 4 semitones. And then rather than going 3 from E to G, I'm going to go from E to G sharp or A flat. And that's 4 semitones. And the reason why I did that, oh, and by the way, when you get back to C, that's also 4 semitones. So this is very symmetric, okay? It's got atonality written all over it. Turns out, augmented triads are used all the time in pop music, rock music, classical music, jazz. Basically, any genre of music uses a lot of augmented triads. So that's interesting, isn't it? Let me just take and map out the augmented triad on our, now this is not a circle of fifths, this is our, as you can see, This is our chromatic scale diagram written in circular format. You know what we're going to be doing. We're going to be calculating a set class, right? So let's take, I'm just going to circle this portion of it, our C, the E, and the G sharp, which is A flat. Now I've written this particular diagram, instead of putting sharps in it, I used all flats. There's a reason why I did that, because it's going to be related back to this diagram, and because I used flats portion of, whoops, I'm just going to fix that real quick. Because I used some flats in this part of the chicken wire diagram, that I have to be consistent here. The next thing we're going to do is we're now going to take that augmented triad and then just click one semitone counterclockwise and build another augmented triad. So I'm going to take it to B, E flat, and G. Well, just looking at this diagram, you can see there's some heavy symmetry going on here. I've got 1, 3, 1, 3, 1, 3. I don't care which way I go, this way or that way, I'm getting 1, 3, 1, 3, 1, 3. So the idea of going through the excruciating pain of calculating the set class by having to take, once you calculate the set class in this diagrammatic form, taking the inverse, putting that into normal form, comparing it to the normal form of this, you don't need to do that. You can use symmetry. And symmetry becomes very useful in terms of reducing the amount of work you need to do. That's one good thing about symmetry. So let's just go ahead and go and do our numbering scheme. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. So I could start here and go up here. I could start at the B and go down to here. Remember, we're traversing the smallest distance of this circle possible to come up with our set class. Set class being an abstract representation of this note form. So let's just go ahead and use, just because I always like to start from the top somewhere, I'll start with 11 and we'll just draw out 11, 0, 3, 4, 7, 8. And then I'm going to want to start with 0 because that's what you do in terms of defining your set class. So we'll just go up a semitone. And there's your set class. And that actually happens to be set class 620. Okay, we're going to use this set class, perform some symmetric operations on it, and show you that by doing that, you can use this procedure that we're going through right now to march your way through these edges and create your own voice leading. Okay? Let's see how this works. So let's remember that 0, 1, 4, 5, 8, 9. Actually, let me do this. Because I've only got a subset of the tonnets here, of this chicken wire representation of the tonnets, I'm going to go up. I want to start with E flat actually, so I'm just going to take it up 3 semitones. So I want to take this up to 3, 4, 5, I'm sorry, 3, 4, 7, 5 plus 3 is 8, 8 plus 3 is 11, 9 plus 3 is 12, which is 0, right? So let's remember that. 3, 4, 7, 8, 11, 0. That's an 11. Sorry. 11. So this is pretty cool because we're going to now use some more symmetry arguments, and I'm going to draw a cube, and we're going to use the symmetry of the cube to it'll be revealed. I don't want to tell you yet, but it'll be revealed what's going to happen here. You need to draw it in 3 dimensions so that you can see what's going on here. Yeah. There we go. Now I'm going to do the back side in dashes, just like an architect would do. Okay, there's our cube. Now I want to label the faces of the cube with these numbers, kind of like a dice. Okay? And I'm going to label the top as 0. Okay, I'm going to label the back of 4, and what I'll do is I'll put it in a dashed 4 so that you know that's the back side. Okay, so because it can get a little confusing here, it's a little tight. So let's do that. And 3, we'll label the front of this 3, and then we'll label the back side, the bottom 11. Once again, that's going to be in this format, and then we'll take and label this face 8, and then the last face we've got we'll label 7. Whoops, that's in the background, so we've got to label that a dashed 7. Okay, I hope that's legible. It looks pretty good. Now what we want to do is, this is actually yet another representation in terms of you've got a vertex here and then you've got edges. But we're going to use that as our voice leading. So the way we calculate each vertex is by taking the faces of the adjacent that were created by the edges coming out of that vertex. So you just take the numbers that are on the adjacent faces. So for example, if I want to calculate this node right here, this vertex here, I would take 0, 7, and 4. Okay? Hope you can visualize that. If this is my node here, I've got this face, and this face. Just take a dice, find a corner, and you'll know what I mean by mapping out those 3 faces that define that vertex. Those 3 edges that point into, they're also called rays, that point into that vertex. So we've got 0, 4, 7. Well, if I come back to our graph here, I have 0, 4, 7, C, D, E, F, G. Okay, that's a C major triad. We'll put a C there. Okay? Let's march on over to this guy right here. We've got a 0, 7, and a 3. We've got a 0, 7, and a 3. Okay, so this looks like it's going to be minor. I'm going to go 0, 3, 7. So I got C, E flat, G. That's a C minor triad. Here, I'm going to put that in blue to be consistent here. Okay, let's go to this face. 0, 3, and 8. 0, 3, and 8. 0, 3, and 8. Actually, it'd be more like 1, 2, 3, 4. There's 1, 2, 3. Remember, these are abstract numbers. You can change the ordering because I know I'm having to come up with major or minor triads here because that's how our diagram here is defined. So we got 0, 3, 8, A flat, C, E flat. That's A flat, C, E flat. That's A flat major, right? Okay. Now let's traverse down to this corner right here. Once again, it's great if you have a piece of if you have a dice with you, so that you can kind of just look around that and follow what's going on here. Let's take 3, 8, and 11. Here, I'm going to just start erasing some of this stuff. 3, 8, and 11. 3, 8, and 11. 3, 8. That's right, 3, 8, and 11. That's A flat, B, and E flat. That's A flat minor. A flat minor. Not a 9B, but that's an AB. Okay, now what I want to do is I'm going to head over to this guy, which is that space 0. What is that? That's 4, 8, 11. 4, 8, 11. I know this is tedious, and I know it's kind of abstract, but just follow along with me, please, and you'll get this. 4, 8, 4, 8, 11. 1, 2, 3, 4. E, A flat, B. E, F, G. That's like E, G sharp, B. That's E major. Okay, oh, I didn't do this guy back here. Whoops. The one in the way back. Okay, that's why you need to sit in the front of a classroom. You get noticed. Okay. All right. 3, 4, and what? No, 7, 4, and 11. So 4, 7, and 11. 4, 7, and 11. That's E, G, B. That's an E, sorry. It's hard enough to follow, right? That's E minor triad. That's just a little E. Okay, let's do this guy. 0, 4, 8. Oh, geez. Right away. Augmented triad. So 4, 4. 0, 4, and 8. That is, that's just going to be our C augmented triad, right? So that we'll just put C, A, U, augmented triad. Okay. Let's do this, our last guy. 3, 7, and 11. Oh, another augmented triad, right? 4 semitones, 4 semitones. Okay, we got E flat, 1, 2, 3, wait, 1, 2, 3, 4, G, 1, 2, 3, 4, B. Well, that's going to be E flat major augmented, E flat augmented. Okay, now we've built our cube. What do? Well, it's pretty cool. You're going to take some symmetry relationships on this cube. This was a lot of work to get to this point, so let's use what we've done to build something. Okay? You could start anywhere you want on here, but I'm just going to map out sort of a cool symmetric relationship here. I'll do it in red so you can see what's going on. I'm going to start with E, lowercase e. Actually, I'll start back here at this E. It'll make it easier to explain. Make it easier to explain with this E. All right. All right. So I'm going to go from E to A, up to A major, over to C, back to C, and I'll just take it down to E. So you see what I've done? Boom, 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 boom. Okay? That's using the edge diagram of this cube and using some type of symmetric shape here to map out these chords. So now let's start with E. We'll go to A flat minor, up to A flat major, over to, I'm just going to be consistent here so that you know that this is C minor, over to C major, and then down to E minor. Well, let's take a look at our chicken wire representation. If I start with E, lo and behold, look what's happened here. E, A flat, E, A flat minor, A flat major, E, A flat minor, A flat major, C minor, C major, E minor. Well, I'd say you've learned a lot, okay? You've learned about chords. You've learned about set theory, you've learned about the tonnets representation, you've learned about voice leading, and you've learned about now using the chromatic scale to come up with your voice leading based on certain symmetries. This isn't the only voice leading possible. Actually, when you go look up this particular graph, you can see that it becomes much larger. It is like a big chicken wire fence. You can do anything you want. You could do a voice leading. If you don't like this voice leading, do something like this. For example, anything you want. But the point is, you know set theory. So you can create an abstract set, fool around with it, come up with some symmetry relationships, and in a beautiful manner, map out a voice leading, a progression. One that's very unique. This opens up your, this creates you a much larger toolkit for you to do this. Now, could you have gone to this, and you can work back, actually, you can work back in a retro manner too. You can take it here and say, oh, this is my voice leading. What's my universal set class? Well, work backwards, trying to find your set class. And then with that set class, and for example, remember this set class included 6 notes, okay? It turns out that then if you look at the interval class vector of this set class, which I think that it is, gosh, what is it? I forget what it is, but you can look it up. But for the most part, once you know the set class, then you can do operations on that particular set class, and you're going to be able to open up a new world of composition. In fact, let me look up that set class. I've got it over here somewhere on my set class table. That's its set class, 303630. So remember, this is a minor second, minor third, major third. This is a perfect fourth, and this is your tritone. So 1 semitone, 2 semitone, 3 semitone, 4 semitone, 5, and 6. Now remember, when there's a 0 in your set class, that means that you can now transform up 2 semitones. Okay, and you're going to be left, every single note that you have in your original set is going to be different. And that's actually going to play a big role in, once I start explaining what the 12-tone technique is, that's what you call combinatoriality. That's a good word to know, combinatoriality. That means I take 6 notes, and now I want to derive another 6 notes. Can I derive 6 completely different notes from this? And you can just look at your interval class vector and determine that. Now remember also that if you were to go up by a minor third, you would be preserving 3 of the tones. And you can do all this and prove it to yourself, and it's in fact true. Okay, so that's it for today. I thought that was a pretty cool lesson because that's actually a methodology that is used to create atonal music. So that's it, and I'll see you later.